analysis assignment. That's what I'm going to use tonight. I'm basically going over that assignment, but just with a reduced down data set, reduced by number of items or variables as opposed to by number of people. So let me show you what that looks like. I have there's a PDF version. I made the same thing here. This is just the Microsoft Word version of it, but it's the same thing. So why are we doing factor analysis in this class? Well, factor analysis is the root, as we talked about a little bit last time, of all of our latent variable modeling. And we can do a lot with confirmatory issues and exploratory issues of validity and reliability around factor analysis and other models. It's also a really useful introduction as one might start considering some of the ideas in item response theory and diagnostic modeling, which, we'll do a little bit of item response theory in the next class. So in this, for your assignment purposes, let me just kind of run over some of this. This is just a table of contents. If you have this version, you're welcome to pull this up on your, on your end and kind of peer over the table and some of the content in this document. This is just a document that, Sally, you asked to record this. I'm gonna record this. I don't know if you were here at the beginning. I'm recording this now, and then I will post this and share this online with you all as non-public, not as private, but as non-public. So please, I'll share this later on. So here we go. All right, so really the assignment itself is what I'm going to follow here. I just want to kind of go over the high level elements of the assignment, and then we'll kind of get into actually using the SPSS. I do this all in SPSS. It doesn't mean that you all can't use R or SAS or any other, M+ or any other software you want. But obviously, I'm only going to go over it in one package tonight. All right, so for the assignment, what we're going to do is we're going to first do what's called a principal components analysis. Last time I talked a little bit about the difference of the types of analysis. So principal components analysis is just going to be the first type of factor model we learn about. It's going to be on the full correlation model. We're not going to decompose the common variance, which is just in a correlation matrix. That's like looking down the diagonal at those ones. We're going to keep those ones in our first model. And then in our second model, we'll decompose those, which is really just a fancy way of saying we're using other variables to predict those models. So for our first model, it's going to be the most generic principal components analysis, which is sort of the precursor, the starter of factor analysis models. And we're just going to do that on the Wexlar data that I'm going to present to you all. I'm going to go through it so that I can kind of take it step by step, because the next step we'll do an exploratory factor analysis with principal, what's called principal access factoring. And then the last model, and we'll do rotation on that. And the last model we'll do, instead of assuming that the rotation is orthogonal, means uncorrelated, we'll say, well, maybe our factors could be correlated and we'll permit them to correlate. So I'm going to walk you through each one of these steps, show you what they're doing, and we'll talk about what each type of matrix we're producing and what those things mean as we go. For your assignment, really what I'm going to ask you to do is the same types of things that I'm going to show you here tonight, and it'll be recorded, so you'll be able to go back through and walk through this. Hopefully it's still recording. We'll be able to walk back through and practice, basically, is what I'm hopefully, this whole analysis procedures for you to get some practice with factor analysis. Some of the steps here. Step one, I'm basically having you do what's called, for factor analysis, do some preliminary checks. We're going to look at matrices. We're going to look at what's called KMO and Bartlett tests. The KMO is to say, are our factors, we're really looking to see, are the correlations in our data big enough to be bothered to run a factor analysis? And then the Bartlett test says, is our matrix different than an identity matrix. For those that don't know what an identity matrix, it's just ones along the diagonal for a correlation and zeros on the off diagonal. That means we're basically saying, are our correlations big enough and are they different than zero? That's what those two tests do. And if they are, we tend to say that it's okay to run an exploratory factor analysis model. From there, we're going to examine things like commonalities. That's how much variance we're going to account for in our model. We're going to explore those. We're going to explore eigenvalues. I'll talk more about what those are. And then we'll look at things like loadings. Loadings, as I discussed last time, are similar. They're basically how are items related to the underlying factor. They're correlated, and that's what a generic loading is. Then we'll look at other types of matrices. We're going to do things like do a rotation. I'll talk to you why we're doing that rotation. It helps us explain what factors means. And then finally, for that, after we get to the Obelman rotation, it'll say our factors are correlated, and we'd like to account for that in our exploratory model, so we'll do that as well. So we'll kind of walk through all of those steps. That'll be the first three types of factor analysis I do. Then we're going to do another factor analysis on a different data set. It's going to be the same factor analysis actually as step 2. And it's going to be for the purposes of cleaning our data almost identically to what we did in our reliability analysis. Remember, when we looked at items for reliability, we went through item by item and said these items were good, these items were not good. Well, I'm going to show you how to do that with factor loadings instead of item total correlations. The advantage of this is for some of you, especially for those that are going to deal with survey instruments or psychological instruments like Likert style data or other ordinal style data, is you can do this with both dichotomous data, but you can do it with any sort of ordinal data like Likert style scales as well, which is frequently what we use in psychological surveys or surveys for assessment. So it's a useful tool there. Another thing about this whole idea for factor analysis is it's a bridge to you for some confirmatory analysis, but we're not going to be doing that in this class. There's a whole nother class if you get interested. My recommendation for those, if you haven't taken regression, that's a very good course to take, because regression is what you'll need to do structural equation modeling. And in structural equation modeling, ideally, you should be doing some confirmatory factor analysis. All right. Lauren, I see you raised your hand.
Yeah, so I just want to clarify. So basically, you're running through the homework tonight on a different data set, a smaller data set, but that 1, 2, and 3 up there, the different types of factor analyses, we're essentially running, or we're going to be reporting data, items 1 through 8 on all of those, and then item 9 is to compare the 3. Is that correct? In my understanding?
So you will do as much of it as you can for each one. So these 3 models that we're going to run tonight, right now, I am going to run it on the actual data set you're going to use, which is this data set right here. Let me just throw that to the top. But I'm only going to do a subset of those variables, not a subset of the not subset of persons, but a subset of the variables. So you'll put in all of these data that are appropriate as opposed to just the subset. So I will do that for the first 3, for the principal components analysis and the factor analysis models that I run. And then for each one, we're going to kind of go through each step. Now, what I'll say is for things like what is the correlation amongst factors, sometimes that's a little tricky. I already sort of answered that for things like orthogonal rotation. There's no correlation. The correlation is 0. Whereas for when you allow factors to correlate with each other, there'll be a precise answer to that question. So there's, for most of them, you're going to go through, do them for each one, all 9 of these elements for each one of these 3 factors, that factor analysis models we're going to run.
Okay, yeah, that makes sense. Thanks for clarifying.
And then for this one, we'll see how far we get tonight, but this one is going to be a very similar process. We're going to use this data set here, which is just Likert style data numbered 1 to 5 instead of actually having in here, agree versus disagree. Let's see if I have, no, I don't have the actual values here, but instead of, strongly agree to strongly disagree, I just have them categorized 1 to 5. You could, recategorize your data to be similar. It could be 1 to 7, it could be 1 to 3, but the idea here is to show you that we're not just stuck on data sets that are dichotomous 0, 1 category data or 1, 2 categorical data sets. So that'll be, and then part 5 here is really for you to chat a little bit about elements of reliability and validity, about factor analysis. You can be using context from the textbook or from our lectures. All right. So let me just actually open up the SPSS, use some of this. So this is, you have access to this SPSS data set. Your SPSS data set is available to you under lectures. I put it under lectures because this is all one big lecture, really, including your assignment. The polytomist, the Wechsler data that I'm pulling from, the intelligence data is available to you right here. And the polytomist data that I'm going to use as an example is available to you here as well. So let's go to this data set. So I'll try and make sure I stick with I'll probably flip back and forth to the assignment to make sure I'm kind of mapping to the same variables. For your assignment, the difference for your assignment, let me explain to you a couple of these variables. It's not as important, but I'll kind of go to the variable view. Variable 1 is just an ID. It was a client. The first 2 clients are missing. So these are data for individuals. We have them labeled here as client 3, 4. You may see that like 10 to 11, 11 is missing, etc. That's fine. That's just their ID. These IDs, we could have created random IDs instead. This is just general age categories. So these 2 first variables, we would not want to just generically lump into a factor analysis model. These are just descriptive data. This is just an ID, and this is just something about someone's age. So let's ignore those variables for now when we would run a factor analysis model. For everything else here in our data set, here are different subsets of we can see that the raw data here, we have numeric data, and we have different subsets of our intelligence tests, information, comprehensive, arithmetic, and you can go on down the line. If you know a little bit of something about IQ tests, that's fine. If not, that's okay too, because we're sort of more concerned about the mathematical model for factor analysis purposes. So each one of these variables, each one of the, I think 10, 11, actually I highlighted 3 to 13. Each one of those variables is actually sort of a subset, a subdomain of another analysis, but that's okay. We're going to run our factor analysis model on this. So you would have gone through, someone may have had 4, 5, 20 questions under arithmetic, and here's their score on that domain. So we're going to take these because we're interested to see how these underlying items, these underlying variables will relate to each other. Do they build factor structures? If we had good, strong theory, which we actually do in this case, if we have very strong theory in the literature, we might also be able to move to things like confirmatory analysis. If we don't have strong theory in the literature, we start off usually with exploratory analysis like we're going to do tonight. Exploratory analysis allows us to use the data that we have and to explore it to see what type of factors and what type of relationship variables will have to those underlying factors. So let's go ahead and get started. So we have in our practice example, let me make sure let's see, information, arithmetic, digit span. Let's put some of these variables in here. I'm going to go under analyze, and I'm going to go to dimension reduction, and I'm going to click on factor. In case you're following along. If you're not, that's okay too. So I said information, arithmetic, digit span. I think I have block design. Let's see. Digit span, picture completion block design, picture completion block design, and was it object assembly? Okay. For your assignment, you're going to put all of those in. So there's 5 more that you would still be putting into your model. But I use this as a little bit of a toy example. Otherwise, it can get a little unwieldy trying to explain all of the loadings and what's going on in the model. So I now have 6 individual variables that are going to go into my factor analysis model. I'm going to take this step by step. So for our first portion of our assignment and for your work, you're going to start off by looking at descriptives. We can look at univariate descriptives. We can talk about letting it take a peek at an initial solution, make sure that's selected. I think I asked you to look at maybe some coefficients. This will be the correlation matrix coefficients, and then the KMO and the Bartlett's test of sphericity. Again, we're going to say the KMO is going to say, are the correlations big? And the Bartlett's tests are going to say, are they different from 0? And I'll show you what those 2 tests look like. Extraction techniques, we're going to leave the default to start. So your first model, you're going to leave the default too. A principal components analysis doesn't decompose the center, the diagonal matrix of your correlation. I'll show you what that means again. You'll hear that a couple times tonight. For now, I'm going to leave the default extraction methods. I'll say a few things about extraction methods tonight. The first thing I'm going to say is we're going to use, for now, the SPSS default of eigenvalues greater than 1. And the theory behind this is all variables initially start with basically the amount of 1 standardized unit of variance. So when we look to see whether or not one of our components or factors are large enough, what we want to say is they're at least as large as the initial variables that were put into them. That's the theory of eigenvalues greater than 1. There are other and better methods of choosing the number of factors or components we should use in a factor analysis model. And those things are like a parallel analysis, sometimes called Horn's parallel analysis, or different extraction methods like Wechsler's mapping and other methods. But for us for tonight, we're just starting to learn, and in SPSS, those aren't default methods. So we're just going to start by using the very simple method of our eigenvalues greater than 1. And also at certain times, we may choose, I will have you in the second part of the later part of tonight's lecture, when we look at a fixed number of factors, we might just say, hey, I know I just want to look at 1 factor or 2 factors. You could select that here and put the number of factors you want to extract. All right, so I'm going to leave the default. I am going to ask for a scree plot. Scree plots are eyeball tests to see how many factors we might really have in our model. Just because we ask for the default here of a selection criteria, the scree plot is another method of helping us determine how many factors we really believe are in our data, our underlying data. The rotation, I'm just going to open it this time. We're not going to do any rotation. We're going to leave it as none. But what I'm going to do is I'm going to ask for loading plots. We'll see what those look like as we go through the lecture. So I'm going to select loading plots. Later tonight, we're also going to, in our second model, we're going to check Varimax rotation, which is what's going to give us orthogonal uncorrelated factors. And then our final factor analysis type model that we'll run on this data set, we'll use direct Oblomin. We'll leave the default as 0. That'll give us the maximized correlation we can get amongst our underlying factors. I'm not going to do those yet. When we come to that, I will explain that again. I'm going to go ahead and click continue. I'm also not going to do factor scores now. For your last assignment, I asked you to do, I think for your last assignment, I asked you to do a little bit of factor scores and do some default regression model scores. What these scores do is they create hypothetical scores so that gives a person a value on your underlying factors. So it's kind of cool that you can kind of create people scores, person scores for the underlying factors that exist, whether you have one factor, two factors. So we can do that. And there's 3 different methods. We're just going to use the default regression model later on. I'm not going to do those now. And under options, there's really nothing to do here. These are just some missing value issues and other things we're not going to worry about. So I'm going to go ahead and click OK. And I'll try and make sure this maps up to my assignment I have for you. But let's go ahead and click OK and open up our data. Let's take a peek to see if it looks about right. It does. And I'll go to our assignment. I'm just kind of paralleling our assignment, making sure what I ran here. And also for your assignment is another learning tool, by the way. If you look in this assignment, I go through this assignment and I have written dialogue about each one of these. So if you don't get it in tonight's video, if you don't get it in recorded videos, there's more information in this sort of manual of running a factor analysis that gives you a little bit of detail. Let's see, we've already run through most of these. Yes, we've already clicked OK. And I'm sort of just verifying that I have the same data here. Let's go ahead and open that up. Yeah, looks about right. All right. So the first thing that opened up is my descriptive statistics. Use descriptive statistics as eyeball tests. As you get better in statistical analysis, your descriptive statistics tell me things, when I look at means and standard deviations and people that are included in the analysis, I know I have 175 people included total. I have means all between 9.5 and 10.9. They're pretty close to each other. These means are intended to be pretty close to each other the way this testing is set up. And the standard deviations are spot on because it's a mathematical computation sort of in creation of these variables. So what I would expect to see sort of like as you do a as you might have done some sort of variance analysis and analysis of variance to determine whether or not your variance and standard deviations are similar to each other, just like that. For this test purpose, we expect that to be true. For other factor analysis models, that might not be the case, but I know something a little bit about this data, so I'm taking a peek at the means and standard deviations just to make sure it makes some sense to me, or to give me, if I didn't know much about the data, on the flip side, then it gives me a little bit of information about the means and the standard deviations and the number of people included in my data. The correlation matrix. Remember, I've said several times in lectures, in class, and maybe in the factor analysis recorded video, your correlation matrix is a standardized variance covariance matrix. I know you've heard me say that a few times. One of the reasons I'm restating that again is because when I talk about the amount of variance each item brings for information, for arithmetic, for digit span, we are literally talking about on the diagonal of this matrix is their standardized variance. It's all standardized to be 1. On the off diagonal, those correlations are their covariances. So information has a covariance or correlation, standardized correlation with arithmetic is almost 0.5. When you are evaluating correlation matrices, if they don't get too big, if they're not too much out of hand, 10 items, 11 items, I think I said we have 11 items for tonight's lecture. That's not too big to kind of eyeball quickly. When you get 100 items, it's just too large. But with a quick eyeball test, what I'm really looking for is that my correlations, I at least have some correlations that are maybe close to 0.3, 0.4. Even the 0.2s aren't too bad, but I don't want to see a whole bunch of things that look like this, 0.073, 0.035. It's okay to have some in there, but if all of my variables were like 0.05, 0.08, this is the eyeball version of Bartlett's test. It's basically saying most of my correlations, if they're very small, I probably am not going to be using an exploratory factor analysis technique. Whereas if they're relatively large or medium, 0.3, that's a solid correlation to be using for factor analysis. 0.4, 0.5. So we have several correlations in here that are over 0.3. You can see 0.399, 38, 36. We see a 0.4, a 0.3, even some of these 0.2s. That's our covariance. Without some of that covariance, we don't have factors. If all of our covariances were 0, we would have each item would effectively be its own unique factor. It would have no relation to any other item. So if we had a diagonal matrix with 1s, and on the off diagonal, every single value was a 0. That is the definition of an identity matrix. We'd also say every single one of these items, all 6 of our items, if there were 0s on every single one of the off diagonals, all of our correlations are 0, all of our items are uncorrelated. That is the concept of orthogonality. We're actually, for our first couple models, when we say we don't want our variables to be correlated to each other, we are forcing the idea of orthogonality. I mean, we don't want our factors to be correlated to each other. We're forcing the concept of orthogonality on our factors. So in our second model, when we run that, I'll talk more about that again. But that way you have a little idea of an eyeball test for a correlation. If you don't see moderate size correlations, at least, 0.2 and 0.3, you're just kind of wasting most of your time. So in the Kaiser's test, we like to see, 0.6 is fine. We'd like to see maybe 0.6, 0.8 for Kaiser's test here of sampling adequacy. This is just saying for our sample size here, for our data, that we have a reasonably large enough correlations that if we run this model, we expect that some factors can crop up in exploratory models. We also see Bartlett's test is significant here. We have that means, though, that's good, because that means there's a difference between this matrix and an identity matrix. So there's a difference between this matrix and a matrix that would have no correlations. So this is 2 different ways. These 2 tests are 2 very simple ways of saying, is our correlation matrix and our data that's underpinning that correlation matrix, is it adequate enough to run a factor analysis? And the answer here is yes. A couple of red flags for you would be if the KMO were small, like 0.5, and this were significant, Bartlett's test of sphericity were significant, we would have some problems. We probably would not. I mean, you could run the model, but you're going to have trouble already to start. We run this data analysis. We ran this. We started it off with raw data. Sometimes we could also just use a correlation matrix. So really, in the back engine of SPSS, SPSS is actually using your descriptive statistics to get variance components and your correlation matrix to actually get a variance covariance matrix, and it's running the analysis on that. So that's true for your general factor analysis model. We'll talk a little bit when we decompose the diagonal, when we change what's on the diagonal before we start. We'll do that in our next analysis. Our communalities. Let me explain communalities again to you just a little bit. Communalities, initial communalities, notice they all say 1. Because our initial communalities are literally based on this diagonal here, the correlation matrix. So the amount of variance I start with in this model for those communalities, for each one of those is 1. So the amount of information I'm putting into the model is 1. The amount of information I'm extracting out of the model, after I run my factor analysis, after I limit the factor analysis to having a smaller number, potentially smaller number of components or factors than initially started. So we initially started with 6 variables, and when we're done, we're going to have less. We're actually only going to have 2 factors. With that reduction, we still account for an amount of variance, which we call communalities. In this case, we're still going to count for like 0.663, 0.618. We're still accounting for some amount of variance in the model. It's just not the full variance, nor should we be. Because what we're doing in a factor analysis is we're trying to, from an exploratory model, from a principal components analysis, this very first analysis. The big distinction between a principal components analysis and a factor analysis, first, is I'm not rotating, and it's about trying to really reduce our data down. It's our first look to see, can I even reduce this data set down to any sort of meaningful component or factor? And here, as we go down, we sort of get the answer yes. And I say sort of. We have reasonably good initial eigenvalues. Each eigenvalue tells you is going to tell us a little bit something about each component. Mathematically, by default, when you run a factor analysis, when you run an exploratory factor analysis model, in theory, initially, when you very first run it, it's a mathematical procedure where you're sort of taking and rotating around the variance in space, the amount of variance that we have, to try to maximize the first component. We're going to take as much in component one variance as possible, as we possibly can get, out of all of the entire variance covariance matrix. So basically, we're taking this matrix here, our correlation matrix, and we're trying to create one component that explains that entire matrix to the best of its ability. That's like factor one or component one. Next, given that we have an orthogonal model, our second component, and we'll talk later about them as factors, our second component maximizes the amount of variance, but it remains orthogonal. So these two factors, or these two components, initially, they are uncorrelated to each other. And so component one maximizes the amount of variance we can obtain from that model. Component two maximizes the amount of variance that can be extracted from this model, but it remains orthogonal to factor one. And then we add another component and another one and another one. And each time we go through, we maintain orthogonality so that the factors are uncorrelated to each other. If you recall, when I initially ran this analysis, what I asked for, I'll just go ahead and open it, is that under extraction, I said, only give us, only retain, only extract eigenvalues that were greater than one. So only extract, so what we're really saying is, if for component one, if the amount of variance it still accounts for is over one, we're going to keep it. For variance two, if the amount of variance it accounts for is over one, we're going to keep that. And when we get to variance three, for component three, we can see that it is under one. We did not keep that as one of the extracted components. So we only use two components are only extracted for this model, component one and component two. But what's interesting, we can see that component one, just the first component, accounted for 37% of the total data. That's like saying component one, we have 1, 2, 3. We can see that we have 6 variables. We have 6. We have basically the amount of variance we initially started with is 1 for each of our extracted variable. Along the commonalities, we can see we could add those up. Those are also going to equal to 6. So the total amount of data we could have had here is going to be 6. Well, our first variable is 2.2. It accounts for 37% of all of the data that went into the model. So component one, if we were just to use component one, it accounts for over a third of our data. So it accounts for the equivalent of 2.2 variables. Component one sort of now, in an anecdotal way, has a value of 2.2 variables. So the amount of variance information brought in was 1. The amount of information arithmetic brought in was 1. Each one of these variables brought a variance to the data set of 1 in a standardized world. Once we've rotated it around and done our analysis, component one has 2.2. Component 2 has 1.3. Component 3 only has 0.77. That means component 3 has less information than any one of those initial variables started with. That's why we're not going to use it in our next stage of modeling. So you'll see that I extracted out component 1 and component 2. I didn't do it. I just clicked a button in SPSS. SPSS did that for us. Let's take a look at the scree plot. This may also help explain what's going on with some of our eigenvalues. Our eigenvalues are plotted in space here. So this is just, SPSS has taken components 1 through 6 and plotted them. We can see along the line, here's components 1 through 6. And here is the specific value for each one. So component 1, component 2, component 3. And we could take this one line and say anything over this line is something we're going to consider investigating. In scree plot analysis with your eyeball sort of looking at this, we'll also talk later on about bends in the scree plot. Here, there's not a great big bend in the scree plot simply because we don't have that many variables and there's not a very sharp turn. The scree is sort of the junk at the bottom here. Sometimes in scree plots, we look at them as a cliff and where do you fall off the cliff? I'll show you a really good example of that when we're doing some of our analysis for our second data set. But this gives you an eyeball test of what your components look like plotted. And then finally, we come to our component matrix. Our component matrix, mathematically, we've asked for 2 components. We have not rotated this. This is not a true factor analysis. We can think about it as a factor analysis, but really so far it's just a data reduction technique. We have component 1, component 2. If it helps, you can think of them as unrotated factors. So we have unrotated factor 1, unrotated factor 2. And these values, these components, are the correlation of the item with the underlying component, or the correlation of the item with the underlying factor. So what we like to see is kind of a minimum. You'll see different throwaway numbers when you kind of go into the literature. A very bare minimum is around 0.3 or 0.4. We like to see loadings. We like to see these loadings is what we're calling them. We started talking about that in last class. Our loadings, our correlations with the underlying components, we like to see those values to be at least around 0.3 or 0.4. In some literature, for strong factors, you might see things like 0.7. But in general, when I first start to look at these, I kind of take a rule of 0.3. And if anything's lower than 0.3 in an absolute magnitude, then I say it doesn't load. We can see all of these for both component 1 and component 2, in an absolute sense, have correlations with the underlying factor. That means these are all really pretty good components for our underlying, I mean, these are all pretty good items to use for our underlying factor. A bad item would be like, imagine that there were zeros on both of the information. If information was 0 on component 1 and component 2, that means it wouldn't correlate with either factor, which means it's probably not a very useful item to be using in my analysis. Let me show you what those components look like in space. I've taken component 1 and component 2, and we've plotted them in space. This is going to give us some intuitions about why we rotate in factor analysis. If you take a look at how component 1 and examine it here, we see component 1 has values of 0.7, 0.6, 0.4, etc., down to 0.5. Component 2 has positive and negative values, and they're all around that 0.4, 0.5 level. These load very high on 1, but they don't discriminate. These load high on 1 and low, for component 2, I'm sorry. The first 3 load as a positive, the second 3 load as a negative. And we can see that in space here. That is in the component 1. Here's this horizontal is our component 1. I'm sorry, our horizontal across here is component 1, component 2 is here. We can see in space, if we were to circle these, actually I do that on there. You pull it up here, I think I have those circled on here. Oh yeah, so it's just the same. So this is just the same as our SPSS output, just a little bit. I default my SPSS, tend to try to use as much APA style stuff. Here's just a default SPSS graph. So component 1 and component 2, we can see that it splits it up well, but on component 1, we see that this deviation here, the split across, they're kind of all nested here, so that all of those values are high, but they don't split well. What we're going to do in the next step is we're going to rotate. We're literally going to take these two values, and we're going to rotate them in space, still keeping them orthogonal to each other, but we're going to rotate them to try and be able to explain what those underlying factors look like a little bit better. So let me come back to our matrix here. So I sort of show you this as your traditional factor analysis. This would be a principal components analysis. I like to start with a principal components analysis and factor analysis because it sort of gives you the idea of where our correlations, the link from our correlations to our communalities, and from our communalities, why we should believe that the variances that we're collecting are even bigger than what we initially started with, why they're meaningful. And eventually, we're going to now rotate. We're going to rotate for the very simple purpose that we want to be able to explain our underlying factors. We're not just going to use them for data reduction. We could stop here. That is, if all you cared about was a data reduction technique, you don't care necessarily about explaining the underlying factors. You just care about saying, I have these 6 variables, and I would like to reduce those down to as many variables as I can within reason. Then you're just concerned with the data reduction technique. Now, why might you do that? You might be looking to reduce down the number of variables in a model to be put into something like a correlation matrix or a regression analysis. So you might use a technique like this for those purposes. There's better ways of doing that, but historically that was a reason why people might use principal components analysis. For us, we usually want to be able to explain some of these models. So we're going to go ahead and do some rotation. In your homework assignment, so all of that which I just did, step by step, is available to you in the homework too. I don't just do the homework for you. I actually, in the manual, step by step, I go through and I tell you each one of those steps. I explain it to you just like I did on a video, but in class, it's easier to chat about it or show you what that actually looks like. In your assignment here, we won't have time for this tonight. I also show where the communalities are coming from. Communalities are just squared loadings added up across. So this component matrix is identical to the component matrix I just created here. So when we look here, I create, or it should be in theory, maybe there's a slight difference here. Nope, it's the same. So this component matrix I just extracted out of SPSS. I squared these values. When I say that, I mean I went to 0.706, I squared that value. I went to 0.405, I squared that value, I summed across, and those values, when you sum across, those will give you our actual components. So let me just make sure. I think I skipped down to our second example. Let's see. Let's go up to, or maybe not. No, okay. So this was the end of example 1. Let's do example 2. Actually, before I do that, I want to show you a couple of things in SPSS. I'm going to reanalyze the data. There's only one different thing I'm going to do. I'm going to go to extraction, and instead of telling it the default, I'm going to say, give me 6 factors. That's the maximum number of factors I could ask for. There are 6 variables going in. The most factors I could possibly ask for, the most components or factors I possibly could ask for is 6, or at least, based on principal components now. So we're doing everything else is default the same. I'm even going to leave for now principal components. I just want to show you something. That is, when I run this model, I analyze this data. Descriptives are the same. Correlation matrix is the same correlation matrix. Same Bartlett test. For your homework assignment, every single one of these models on the same data is going to give you the same Bartlett's test. So you only have to report that one time. Notice the communalities initial and extraction are the same. Because when you ask for the exact number of factors as you started with the number of variables, you're just actually extracting out and toggling around your data, so you will still end with 100% of your variance. This is not actually that useful for the types of techniques we're going to do. I just sort of wanted to show you that you could, in theory, have one factor or one component for each one of the initial variables you started with. The trouble is, by the time you start to get to some of these components or factors toward the end, all you're getting is nuisance data. You're getting the mess. You're getting the measurement error out of a lot of these data, out of all of these variables. So these variables, when you look up here, you're starting to get like component 6 has less than half of the initial data as any variable would. You'd be better off using the initial variables you started with. I sort of just show you that so you can see that at least in theory that's possible. I could have also gone in here and just asked for one factor as well. Lauren, I see you have your hand raised.
Yeah, so when you do that, the whole point of this factor analysis is the data reduction, right? So it wouldn't make sense to put in the 6 because that's the same number of variables that you started with. So we're looking to reduce, and the number of components is what we're reducing it to. Or am I
No, you're correct.
misunderstanding? Okay.
I showed you this because in theory you can do this.
Okay, yeah.
And in theory, if we really had one factor for each, or one component for each one of the variables, we'd be better off using the initial variables. That would probably look like an identity matrix is what would happen if we extracted, initially. But I just show you that because mathematically we can do that. And for those that maybe stay in the latent variable modeling space, there are some subtle reasons why from a components analysis, a principal components analysis, you might want to do this. For factor analysis, we never really want to do this. So let's kind of jump into, let's bridge the gap from what we were doing as a components analysis to a factor analysis. I'm going to do this in some steps for you. The next step that we're going to take, and you're going to do in your homework, is we're going to do a factor analysis. We're going to leave our descriptives the same, except I'm going to go ahead, I think I do this in this stage, I'm going to ask for the reproduced matrix. The reproduced correlation matrix, it's going to take the factors that we extract and try to create the best correlation matrix it possibly can from the factors that we extract as opposed to from the original data. So it's another way after you're done is sort of saying, hey, how good was my exploratory factor analysis? Some people like to look at the reproduced correlation matrix. So we'll take a peek at that. Extraction methods. We are only going to use tonight, we're only going to use principal components analysis and principal access factoring. A useful technique, and as you move, is maximum likelihood as well. As you move toward confirmatory factor analysis, all of those models you'll probably run in confirmatory models will be based on maximum likelihood estimation, based on what you're doing in confirmatory models. It's a useful tool. We're not going to get into that tonight in tonight's lecture. We're just going to be focused on maximum principal access factoring. And I'll describe to you the difference between that and what's going on in principal components analysis. Actually, part of the reason I just run a principal components analysis is just so I can juxtapose the difference between those two. All right, I'm going to go ahead and click continue. I set this back to eigenvalues greater than 1. And I will go ahead and do the rotation as well. I am selecting Varimax rotation. Again, Varimax rotation will rotate the components that I have, the factors that I extract, but it will retain orthogonality. That means it will take the axis that I created, the axes, the X and Y axes that were orthogonal to each other, and maintain that orthogonality so that the variables, the factors that are created from this are still correlated to each other with a 0. In our next step, we'll do some correlated factors. All right, those are the only changes I'm going to make. So really, I just went in here. I asked for principal access factoring. And we asked for reproduce matrix and a different technique as opposed to no rotation. We're now going to rotate our data. So now this is what I would call a true exploratory factor analysis. When somebody says they've done exploratory factor analysis, this is actually the default. That is, if somebody said to you nothing else, the assumption should actually be, now they should tell you the details. If you're reading a paper and they don't explain to you their extraction method and their rotation method, well, shame on the editors for not asking for that from and the reviewers for not asking for that, but shame on the researchers too, right? You should state the method of extraction, you should state the method of rotation, but typically when somebody says, I did an exploratory factor analysis, what they mean is they decompose the correlation matrix, which means they should have done a principal access factoring, and they did some method of rotation, which the default should be an orthogonal rotation. So we'll go ahead and click OK and do that exploratory factor analysis. So this is analogous to step 2 on your homework assignment. This is just the second principal access factoring, explaining the structure with orthogonal rotation. And earlier on in your assignment where I say, do exploratory, so we did a components analysis, now we're doing exploratory factor analysis, and we're doing Varimax rotation. So let me go ahead and click OK on that model. Go. All right. So for descriptives, it's the same. You don't have to, for each one of these you run, on each factor analysis you run, you don't have to give me another descriptive statistics and the correlation matrix again. I'm running them for you again, but you could stop running them after your first model if you wanted to. They're going to be the same, right? So our Bartlett's test is the same. Notice the 0.668. It's because it's run on the default data. These are all like preliminary analysis for any of the factor analysis models that we would run. We have less initial common variance than extracted for some of these variables. How cool is that? What's happening here is that instead of starting with 1, what we are doing is in the background, principal access factoring is effectively trying to predict the amount of variance using all of these other covariances. So it's taking like the relationship of information with arithmetic and information with digit span and picture completion and information with block design and information with object assembly. It's taking information and all these other correlations and trying to recompose from that the commonality. It's similar in some ways of saying this is like the reliability measure for if we were to put these on the diagonal, instead of having ones on the diagonal, we would then place this 0.328 for information is placed on the diagonal instead of a 1, and we call that a decomposed matrix. That is the only difference between principal access factoring and principal components analysis. With a principal components analysis, we use the original matrix. With principal access factoring, we're basically, you can think about it as you would with a correlation, like with a regression model. You're using all of these other correlations to try and predict information. And you're using all of these other correlations to try and predict the diagonal for information. And we're using those predictions as the diagonal value instead of the initial one. So here along the diagonal of your composed matrix would be 0.328, 0.296, 0.133, etc. So those are the initial variants accounted for in our model, the initial commonalities in our model. The extracted method, it can be higher because we're using that entire data set, including those initial values along the diagonal, to try and recreate our model and try and see how many factors we have. So it's the same exact analysis. It's actually the same exact mathematics, but kind of done on what we call a decomposed correlation matrix. All right. Notice a few things here. Our initial eigenvalues, and I have this also for those that are following along in our probably page like 16 or page 18. If you're following along sort of on the in your notes here, in your homework assignment notes, the initial eigenvalues and the initial sums of the initial extracted values, if we go through and we go back to, let me put this over here, we go back to our last analysis that we ran, or the first analysis we ran, we can see that we extracted 2.2 and 1.3 for our first two components. And we can see that the initial extraction method, let me go back down to, here we are. It shows us the exact same initial eigenvalues from the components analysis. In our extracted sums, this is from the 1.647 and the 0.73. This is from the decomposed matrix. So those values, even though it still reports them as a percent, those values are pretty big and meaningful because this is from that decomposed matrix. The rotation in space, notice these two will keep the same total amount of, so we have our initial eigenvalues. They are identical. We can see in the scree plot is identical to the principal components analysis. So the initial eigenvalue columns here are the exact same thing as the principal components analysis. The extracted value is from the principal access factoring. So we've made a selection choice based on our initial principal components analysis, just gives you the initial extraction. Once we decide that we're going to extract out those two, we use principal access factoring, which has reduced down that, all it's done is reduce down that correlation matrix. And now we extract out two factors, factor one and factor two, and then we rotate them. Notice the total percent for factor one. Now this is factor one and factor two. We can kind of go across. We see a factor one and factor two. Prior to rotation, we're accounting for 1.6 and 0.73 proportion of variance. We can see that that's a total of 39.6. We can see after rotation, it's the same percent. It's supposed to be, because all we're doing is taking the exact same amount of variance and we're rotating it in space. So we'll see what that looks like in a second. The scree plot is identical. Again, you don't have to produce this again for me. It's just a scree plot. It's our initial step for determining the number of factors in our model. Instead of a components matrix, we now have a true factor matrix. This is a factor matrix prior to rotation. So it's an unrotated matrix. For factor one, would anyone like to take a shot for factor one? So these are real factors unrotated in space. For factor one, you don't have to chime in unless you want to. I mean, you're welcome to. Factor one, I sort of look at, I was like, how could I explain factor one? That is, I know that these factors, this factor matrix, these are effectively the correlations of a variable with an underlying factor. Well, all those correlations are positive, 0.3, and they range from about 0.3 to that 0.67. Prior to rotation, how would we explain that? We would say things like, well, they all load, that is, they all correlate with the underlying factor, factor one. What about factor two? Does that seem a little bit easier to explain or harder to you? To me, it's a little easier, right? I mean, at least there's negatives and positives. I can say something about, at least, I can say, well, like, these first three variables have a negative relationship with factor two, and these second three have a positive, but so does it in factor one. It's convoluted. It's hard to explain. It is difficult to explain an unrotated factor analysis. This is exactly the reason I show this example too, is this is exactly the reason we like to rotate our factors. So when I have a rotated factor analysis, I'll come back up to the reproduced correlations. The rotated factor analysis is extremely helpful. I've rotated in space until I get to a maximum amount that I can kind of explain. Varimax rotation rotates it around, and it's trying to give us the maximum amount of explanation possible that we can get. So we can sort of see that item one, item two, and item three, they all correlate high. They all load high with factor one. Items 3, 4, and 5 all load relatively low. And conversely, items 1, 2, and 3 load low on factor 2, and items 3, 4, and 5 all load high on factor 2. This is a clean rotation. You won't always get a clean rotation. On your homework assignment, you'll probably get a pretty good rotation in space, just like we did here with the full data set. Here, in your previous unrotated data, this was difficult to explain. Factor one, the stronger factor, the larger factor, had no real great explanation. Everything just loaded on it. And factor two, everything loaded on it relatively high, but some were negative, some were positive. It would be difficult to intelligently talk about these unrotated factors. But for the rotated space, I could start to try and say things like information, arithmetic, and digit span correlate to underlying factor one. Maybe factor one is some sort of mathematical competence factor. Maybe it's some sort of mathematical ability factor. Maybe factor two, picture completion, block design, object orientation. Maybe if I know a little bit about something about those variables, maybe it's something about some sort of spatial ability for factor two. Now, I have not just mathematically separated out components. We're now looking at the rotated factors and getting some, as experts, we can look at these from an exploratory perspective and say, well, these start to separate and start to make sense to me. This is the very purpose for exploratory factor analysis, to be able to reduce down your number of variables to a number of factors, and to be able to start to say something intelligent. And we like to see three loadings. If you ever get into confirmatory models, we like to see three factors for three variables for each factor at least. And here, what it starts to tell me is that information, arithmetic, and digit span tap into the underlying concept maybe of what I'm going to call right now mathematical ability, factor one. And this last three, picture completion, block design, object orientation, they tap into the second factor of some sort of spatial ability. I now have two factors about persons that I can look at and I can say these items correlate, relate to them. And when I measure those items on a test or a survey instrument or a psychological evaluation, I can say that they relate to the underlying factors I'm interested in. The transformation matrix, I'm just going to talk a little bit more. Hopefully that made sense to you all, that you can see that that was kind of an obvious rotation. The transformation matrix is simply the mathematics. I'm not going to have you do this. If I ask for it, this is kind of extra if you get into this a little. That is the mathematics of how I go from transforming from this unrotated matrix to this rotated matrix. I just do a little bit of matrix algebra. The Varimax rotation uses these values to transform from rotated to unrotated. If that doesn't make so much sense to you, that's okay. It's just how we went from rotation in space from initially, I'll go back up here a second, from rotated in the initial extracted values would have looked something like our initial communalities, our initial factors we had, which looks like this. We couldn't explain this well. Now, in rotating it in space, what it does is it allows us to see these clusters. The clusters have stayed the same, but it allows us to say, well, if I were to take trajectories of each one of these items onto factor one, there's going to be a big difference where these three clusters land on factor one and where these three land on factor one. And on factor two, if I take the same three clusters and kind of project them down onto factor two, and I take these same three and project them down on the factor two, those clusters are separated in space. So what that does is it takes this two-dimensional space of rotated factors and it creates the three-dimensional space for us. This is how these three items hang together in two-dimensional space. And this is how these three items hang together in two-dimensional space as well. Three-dimensional space, you'll probably be able to, take a peek at later on with boxes. Once you start getting to 4 and 5 dimension, factors, it becomes harder to really plot your data and understand what it means. It's not impossible. We can, you can mathematically do it, but usually visually, it's very difficult to get beyond 4-dimensional space just on a 2-dimensional surface. So anyway, this is this rotated factor matrix displayed for us. Let me just come back to one thing. Our reproduced correlations. I have been saying to you, and some of you maybe have, not quite gotten the idea of what a decomposed matrix is. Let me go back up initially. Let me look at these values along the diagram: 0.57, 0.43, 0.19, etc. Go back to the initial communalities here: 0.57, 0.43, 0.19. The communalities that we ended up using are from our reproduce. We tried our best. Basically, we're trying to create a reproduced correlation matrix. We are trying to reproduce the correlations, the communalities, the reproduced ones go along the diagonal. And then we create a reproduced correlation for arithmetic and information. We can see that we are negative 0.00003 away from the initial correlation. So if we went to this 0.498 and we go back to the initial correlation here, we can see we had 0.494. We're pretty close to that value, right? We can see that 0.323, still pretty close. A couple of these might be off a little, like block design and arithmetic are off by 0.065. But in general, we reproduce that correlation matrix pretty well. Let's talk about the very thing, in your recorded lecture and in our last lecture, which we spent a lot of time talking about the very idea that factors underlie the correlation matrix. If factors really underlie, if factors like from our lecture, if the factors that we have really underlie the reason why these correlations exist, then of course we should be able to reproduce our correlations from a limited number of factors. So here we took 2 factors and we reproduced the entire structure of our correlation matrix pretty well. We did a pretty good job. So this is another eyeball test to say, did my factors actually do the initial job they're really expected to do, which is saying why, the initial thing we're trying to say, we have a correlation matrix. This is just you ran a correlation. Why do those correlations exist? That's it. That's the question you're really asking initially. And I say to you now, after running this model, they exist because after running an exploratory factor analysis, after rotating my factors, I have discovered there are 2 factors. There's a factor for mathematics ability and there's a factor for spatial ability. And it underlies this initial correlation and it gives rise to these correlations that exist. And when I went to reproduce it, I did a pretty good job of reproduction. So that's one of the ways you can kind of tell. If we started seeing correlations of like, the residual correlations here that we were off by like 0.1, 0.2, we'd be like, well, maybe we didn't do such a great job. But that's one way of sort of just kind of eyeball testing, seeing whether we did a good job. Another thing that I can sort of say is, oh, Lauren, so you have a question.
Yeah, so you keep saying that like the one is the mathematic ability and the spatial ability maybe for factor 2, but you're just making those up,
I
correct? Like
am. I'm making them up. I mean, I
okay.
know a little bit about, IQ. I am
Okay.
making them up, but we started this semester with the very idea that all factors that are ever created, all underlying latent variables are constructed, right? We, as education, mathematical ability, what is mathematical ability? Well, here I'm saying the underlying variables that I'm giving rise, each one is related to mathematics, and I'm calling this factor, I'm making it up right here on the spot. I'm calling it mathematical ability. What
Can
else
you
could I do to verify that? If I wanted to
uh
really call
Other
the
research and stuff, right? Like, or some
yes.
experts and stuff to validate it.
Wouldn't we go back to this test? We would say, hey, did we design it to be mathematical ability? Number one. Number two is if you knew something in the literature about digit span and arithmetic, we would know that those were actually created to be related to things like some of your mathematical ability, right? So do you have to know that here in this? No, you can just make something else up. If you called it something else, I'm not penalizing your homework assignment, but typically, if you are running a factor analysis, it's usually because you're interested in the data that you have. And if you're interested in that data, you didn't just extract out data you're not an expert in. I mean, I can do that. I can run a factor analysis on any data, but I can't interpret it. I can run a factor analysis on any data in any field, but I can't interpret it. Here, what you would sit down and do if you weren't the expert, if you were sort of playing the methodologist role, which is what we've done, we would run the model. Then we would sit down with experts and say, I have these 3 variables. They come from this test that I don't know much about. Let's chat about why these 3 variables might be related. Let's chat about why these other 3 variables might be related. And when I do this, because I actively do this, like I take someone else's data, somebody says, hey, can you assist me on understanding what my data are? And I sit down with them and I say, here's the pattern. I happen to call this mathematical ability. What else might you call it? And if you have another name for it in your field, if you have another, you'll start saying, well, those make sense because of, and you come up with another reason. And we would go with your reason as a content expert, not my reason as a psychometrician or a statistician. We would sit down with the experts and we would understand why. Now, it just so happens I pick IQ tests just because historically I've done some work, a little with IQ tests. I know at least enough to be dangerous so I can chat about it in class. Does that answer your question, Lauren?
yeah, I think so. If you go back to the data though, the viewing it,
The
those
raw data?
yeah, I think so. Those factors are not there, correct? Like they came from it separated it out because of the eigenvalues or something like that, that
Eigenvalues,
into
yeah.
eigenvalues into two factors, correct?
Yeah, what do you mean the factors aren't here? Like this is the raw data, right? We're creating those factors. They're the underlying variables we're creating. We created this analysis, right?
Okay, yeah.
These are the factors. This is how we could potentially create those. I'll skip a tiny step here for you. That
Okay.
is, if I really wanted to say, so if you wanted to talk about as you get deeper into factor analysis, remember, this is just our introduction to factor analysis, right? This is just to give you enough tools to start being dangerous and hopefully exploring factor analysis, and maybe get you interested in things like latent variable modeling, structural equation modeling, IRT, item response theory, latent class analysis. It's the whole idea of getting you interested and giving you a small foundation to start. But if we wanted to, we could try to take these factors. If I wanted to in SPSS, I could go to say, well, I would like to know what a person's score hypothetically would be on that underlying factor. And we could go to scores. We could say, hey, save us some factors from this analysis I just ran. Go ahead and give me your predicted score based on a regression method of where somebody, an individual, would be on these underlying factors. I'm not going to display the score coefficient for now. I'm just going to go ahead and click continue and OK. And then I go back to my data set. And I now have produced factor 1. And I can say person 1, client number 3. On factor 1, we estimate them to sort of have a 0.53 on factor 1 and a negative 0.8 on factor 2. Another way, as psychometricians and as those leaning in toward item response theory, we could say this person's, all these factors that were created, factor 1 and factor 2, are standardized. Factor 1 has an average score of 0. That means if you're average, you scored a 0. Factor 2 has the same. These are both standardized variables, and they have a standard deviation of 1. That should give us a lot of intuition. We know that person 1 is above average, slightly above average, half a standard deviation above average for factor 1. So on math ability, they're slightly above average. On spatial ability, they're slightly lower. For factor 2 here, this person has a 1.6 and a negative 1.4. We can go down and we can see all of these patterns on these variables. We can see someone here that has negative in both. Anyway, so this gives you hypothetically a factor score for mathematical ability and a factor score for what I called spatial awareness. You could call them spatial ability. You could call them something else. Now, be careful. Be very careful when you go to make sure you understand your data well. It could be, in theory, when you created factor scores, a negative score could mean a better value than a positive value. It would depend on the meaning of the initial variables. So just be a little bit cautious when you're running those models. Let's take a peek later on. Yeah, here's a positive, here's a negative, negative. So we know somebody might be below average, somebody here might be a standard deviation and a half, a little bit over a standard deviation and a half above average. This is kind of cool, right? This can tell you person ability. This is where that person would lie on the underlying factor. If it were the normal distribution of a 0 mean and a standard deviation of 1. So I jumped ahead a little bit there for you. I don't think I asked you that. So on your homework assignment, I asked you that, maybe I asked you to produce scores. I don't even remember if it's on part 2, maybe. Yeah, I think I tell you to do some factor scores at the end of one of these. Or maybe I don't. But now you know how to do it either way. It's kind of a cool thing. It also leans us in toward item response theory. Let me do our last for the Wechsler test here. Let me go ahead and do our last analysis. We're going to do everything else the same. I'm going to go ahead and do our analysis, our factor analysis model. Descriptives, I'm not changing. I could remove all these if I really wanted to, except I might keep the reproduced matrix. Extraction technique, I'm going to keep principal access factoring, not going to change anything there. For rotation, I'm going to go from Varimax to direct Obelman. Direct Obelman, I could put values less than 0 in here. But what would happen is I would be reducing the size of the potential correlation I have. By putting 0 here for delta, it will maximize, mathematically maximize the relationship amongst my underlying factors. And you might say to me, why would I want to correlate or uncorrelated factors? That's kind of where we are right now, right? So we started with uncorrelated rotation. We rotated them in space. We kept the parameters of our model exactly the same. That is, when we rotate orthogonally, the data that we have, let me go ahead and in space. So this was our initial, this is our rotated in space. These angles stay exactly the same. One way of thinking about correlation in space is just taking the axis and spinning it around until it looks really good. When we do correlations, we actually can change this from being a 90-degree angle to something less. We still reproduce it. It looks like a 90-degree angle, but in theory, we allow our factors to correlate. If they were to correlate 100%, they would actually be the same exact factor. It would only be, if they correlate 100%, you would only need one of those factors. And, it actually mathematically would only pull out one of them. So it would be a little bit of trouble anyway. Let me come back to our analysis. So I'm going to allow them to rotate. We like to see, the amount of overlap. We like to see moderate correlations, again, around 0.3. We square that value. It tells us how much variance is accounted for. I'm going to go ahead and click OK. Click continue here. And scores, I'll leave them on just so you can see what happens when I leave them on. They'll give us another 2 lines of factors that'll be slightly different. All right, so the only thing, again, just to highlight, and if you're following along, I'll just change this from Varimax, which is orthogonal, no correlation. Do I say, well, in the literature, there's reason to believe spatial recognition or spatial abilities, and mathematical abilities are correlated. Maybe it states so in the literature. This is where we're sort of being quasi-confirmatory. We're still using the tool of exploratory factor analysis, but we're allowing maybe ourselves to be guided by the idea of whether or not I should have correlated factors. And I would think that we might want to take a look at those. All right, so I'm going to go ahead and click OK. Again, you don't have to do this. You can just show me this one time. Descriptives, correlation matrix is the same. Bartlett test is the same. I mean, that's kind of easy. You do this test 3 times. All the initial stuff is the same. Our initial and extracted here, when you look at those commonalities, we can see if you take the 0.328 and the 0.296, and we go back up, we can see that those are the same as well. You don't have to re-explain these again. That's because everything's going to be the same in our model until we choose our rotation method. And that's after the fact. It's after we've extracted the values, after we have initially checked the eigenvalues. How big are those eigenvalues? That's the same as the principal components analysis. Then we say, well, we would like to extract out from our decomposed factor axis model, from our decomposed matrix, we extract out 2 components. This is how much variance those account for. And that's still variance compared to as if we hadn't reduced down our matrix. So this isn't so bad. Then we rotate them in space. And the rotation is going to look just a little different. So let's kind of go down if I did it correctly here. We still have our, I mean to be clicking on factor. So we also have our scree plot, looks exactly the same. We have our factor matrix, which is actually starts off the same as well. We come down, let me skip over the reproduced matrix. We now have a pattern matrix and a structure matrix. Before, we only had one of those. We just had a rotated factor matrix. Well, the reason here is because we have I will kind of go backwards here. We have a correlation between our two factors. We have a correlation of 0.31. That accounts for about 10% of the relationship with each other. That's about the minimum we'd like to see and retain a correlation. If this were much smaller, let's say 0.2, 0.1, I might just be suspicious that that correlation is just an artifact of the data, and I might force this to be orthogonal. And when I say force it to be orthogonal, I just mean run a Varimax rotation instead. Here, our structure matrix and our pattern matrix, we can use to interpret our data. I'll kind of use this here so I can point you as you're sort of looking through. Let me pull up the correct. Oh, I went too far. So with oblique rotation, we have our pattern matrix, which we can sort of think of similar to loadings, but they're sort of more like our, I mean, I'm not sure exactly how much regression you know, but you can think of in a regression model, the beta correlations. These are kind of like predictors, like the same way a beta coefficient would be in a regression model, whereas our structure matrix is kind of the correlation, and I might use in interpretation purposes just this same exact way. Let me go back to our factor model. The same exact way I might use to interpret our model last time. So we might say we have a whole bunch, very similar for information, arithmetic, and digit span. They still correlate in a very similar way as they did with the unrotated matrix. And for picture completion, block design, and object assembly, they relate in a very similar way. So these three variables, just like we got in our orthogonal Varimax rotation, it's pretty much the same as we got here. And same when we look at the factor 2, we have variable picture completion, block design, and object assembly all correlate pretty high with that second factor. That's because there's really not that big of a correlation. We look at those let's look at these from a spatial perspective. We see that we actually cleaned it up just a little bit. Rotation does just enough that I might be convinced to retain it here. It's right there. This rotation this example is just on the cusp. That is, it's reasonable to keep that correlation if you chose to, but it didn't really add that much. That is, orthogonal or oblique, we maximize the correlation that we could have gotten between those two factors, and the explanation tends to be pretty similar. These three items, these three variables, load high on our projected factor 2. They load lower on our projected factor 1, and same with these three. They kind of load all in this space here on if we project them down and if we project them across. So it didn't really help that much. But something that's very obvious for good factor analysis models, for the most part, it really doesn't matter the methods we often use for rotation. A lot of times when we force things to happen and we look at it from 3 or 4 different ways, a lot of times it's because we didn't get great interpretation. So you're trying to improve it. But here, something very nice happens. No matter how you decided to rotate it, you want a smaller correlation, you want the maximum correlation, you want the minimum correlation. The explanation's the same, which means the interpretation that we would give to these factors, whether we forced orthogonality, that is, whether these two factors have correlations of 0 or whether they have correlations of 0.3, how we would explain them would be a very similar explanation. That is convergence. We really like to see convergence when we can. So let me go back. One other thing that I ran for this. Notice, hopefully you can see my data. We can see that I ran factor 1 and factor 2. The difference here, let me take this out of the way. The difference here is for factor 1 and factor 2 now, these are on the oblique model. So this is like factor 1 Varimax rotation, factor 2, Varimax rotation. This is where that person would lie on those factors. This is the second analysis that I just ran. This is factor 1, and this is factor 2 on the second analysis, where I permitted those two variables, where I permitted those two factors to correlate to each other. We can kind of see there's a little bit, there'll be some sort of difference, but in general, the pattern is going to be very similar. When you go down, if you were to take a peek at some of these, you'll see the pattern's pretty similar. And if we were to run some analysis here, let's go ahead and do a correlation. Kind of fun to do. Won't be perfect, but it'll be pretty close. This is from analysis 1. I do a little correlation, and we get a pretty low, based on there's going to be some, correlation just because the predictors are being recomposed, but it's a pretty small correlation we get there. When we run it on our second set of variables, let me go ahead and reset this for factors 1 and 2 from our oblique rotation. We can see that the factors are stronger. That's just because in the initial one, when we go to create factors, they're created from orthogonal factors, so we're removing everything but nuisance relationships. And in our second one, we're allowing those two to be maximized with that value. I forgot what it was exactly, like 0.31 correlation between those two factors. So that'll increase the relationship between those when I go ahead and create person scores for each factor. So when we talk about scores on a factor, we kind of created these, right? We mathematically mathematically chose a cut score basically of 1 for our eigenvalues. By doing that, we created 2 factors for this first one where there's orthogonal, and we created person scores. So this is like person score, factor 1, factor 2. We could choose to name these, right? I chose to call them math ability and spatial ability. You could choose to call them something else, whatever you want to call them. But we now have scores on these underlying factors. Not as big a deal when I have 6 variables, but imagine I had 50 variables. Imagine I had 60 variables. In some ways, this is sort of like a doubly, factor analysis, because some of these block design, object, orientation were actually constructed in a different sort of way from another sort of sub-factor analysis, which I'm not going to get to in this class. All right, I see we're running out a little bit of time. As usual, I've said a lot in a very little amount of time, and I just want to go one time through the second analysis, just so you've seen it once on our second data set. So, and I can hang out for a little bit after class is sort of officially over to chat about some of the analysis or questions on assignments and stuff. So this data, as opposed to being a continuous measure, which we often run our factor analyses on, we can run them on, on our, what would be the equivalent here. We're going to say this is Likert style data or ordinal data. So strongly agree through strongly disagree, where strongly agree was 5, strongly disagree was 1. I've got 22 items. You're going to run this model. Actually, I probably do this on the subset, but just for, for analysis purpose, I'll go ahead and run this probably on the full data set. So this is really literally what you're going to be doing in your, so I want to make sure that you really get the idea of how to run this analysis. So we have 22 items. This is a survey instrument. We chose to put 22 items on a survey instrument. That's already a lot of items for people to respond to. When we start seeing 40 and 50 items on a survey instrument, we have to start thinking, if it's our instrument, how can I reduce down the number of items? How could I remove items that don't really matter or are functioning in a way I don't want them to function? Well, factor analysis is one of the ways we can do that. I'm going to go back to dimension reduction. I'm going to treat this the same way as I did before. Item 1, this ID, is just a person's ID. That's the person's values. I just have them ID'd 1 through however, what N. I'm going to take all 22 items and I'm going to put them in as variables into my model. This would be the same as if it were a test with 0s and 1s, but here it's good for us to kind of extend it out into some of the psychological literature. We don't always have 0s and 1s, so here we're going to use continuous or quasi-continuous data. We can still ask for things like univariate descriptives, coefficients, the Bartlett's test, a reproduced correlation matrix. I went ahead and clicked on all of those just to show you can still do those. Extraction techniques. I'm going to start with principal access factoring here. If this were pure, if this were kind of like a pure, just kind of reducing it down to one factor. Now, what might be the case is that I want to take my test, which could still be a test instrument, partial credit instrument, or my survey instrument. I want to definitively reduce it down to one factor. That is a goal often when we want to say all of our items relate to the underlying construct, just one underlying construct. Well, this would be a method of doing that. But for now, I'm just exploring the data. I'm just taking my first peek at the data. So I'm going to go ahead and do principal access factoring. I'm going to let there be take a look at the scree plot and let it tell me the number of eigenvalues. I could do rotation. I think for this example, we're not going to do rotation, and I'll explain why, because we're not going to try to interpret our factors as much. We're really just trying to see, do items load on factors? So for this purpose right now, you could do rotation. I'll click Verimax rotation just so we can see what happens. But that's not really the focus of what we're doing here. I'm not going to do factor scores for now. You could do the same thing. I'll do them. Well, actually, I'll take them off because I'll probably run this a couple times. Maybe the last time I'll click. If I were going to do factor scores, I would just save as variable as I've done before. I'm going to go ahead and click OK. And it's probably going to give me a temper tantrum over rotation, just because it's going to say things like, let's see, did it? Oh, it did rotate, right? Eventually, it will give me a little temper tantrum. I'll show you why. So this basically gives me the means and standard deviations of each item. So it kind of gives me, if I go through, I can kind of just take a peek, and maybe this might tell me, all of the variances. I mean, all the standard deviations are pretty close to each other. The means all seem reasonably close. You could go through this in a little bit more detail. It'd be weird on a strongly agree through strongly disagree. It might be a red flag if most values are 3, and then you see one that's like 1.1, or you see one that's 4.9. That means that for some reason, almost everybody is agreeing or disagreeing with that item, and you might take a peek at what's going on in a little more detail. Here's the correlation matrix. Way too much going on here to try and figure out, right? We don't know what are items big. Is there enough big items? I mean, just the eyeball test, I see items that are pretty large and correlated. That's good. But it's just way too big to get into the nitty gritty. So we go through and we use Bartlett's test and Kaiser's test. 0.959 tells me there is a lot of large positive correlations here. Look, we can just look up there, 0.7, 0.7, 0.6. There are a lot of pretty large correlations in our data, and this is not an identity matrix. So that's sort of a very clear use of Bartlett's test. It's very helpful. Instead of having to look through every one of them, we can just use Bartlett's test as a guide to tell us that instead. Our amount of communalities, we can see item 1, the amount of extraction for each one of those. Then I'm coming down here. We have 22 potential factors. We know we're not going to use those all, but we go through. This is kind of cool, right? We had 22 factors, 22 items go in here, and we know item 1 accounts for 9.5, accounts for over 40%, almost 43.5%, about 43.5% of that entire data set. Just one factor accounts for that. It's pretty large. It's a good eyeball test. We see that after after extraction and rotation, not much happened. How do I know that? Because how do I know that up here? Not much happened after I tried to rotate it. Matter of fact, it barely rotated at all because there's not much there to do. And I'll show you what that looks like in a second. Here's a scree plot. Remember, here's a good looking scree plot from the purposes of trying to determine, just from a scree plot, I can try to eyeball how many factors I should have. Anything in the scree, we think of this as a cliff and a scree. Where do you fall off the cliff? Well, obviously around factor 2, I've already fallen off this cliff, right? If you're going over this is the cliff here. You land, there might be a second factor going on, but there's certainly not a third one. This is, factor 3 is no real different than factor 18. So why would I keep that in my analysis? This is an eyeball test for the number of factors. Here's my initial factor matrix. Well, I can already see some issues that are going on, but I'll sort of run this through our rotated matrix. We can see that after we've rotated, we have a cut. If this was supposed to be, if in theory what we wanted to do is create one underlying factor, something strange is going on here with these items that don't load on the first factor. Let's just say I have a strict analysis I'm trying to build for depression or happiness, or I'm trying to build a mathematical ability. This could still be math ability. Things don't load on factor 1, and they're loading on what I might start calling a nuisance factor. Instead of trying to rotate, I might just say, hey, what would this look like, instead of letting it tell me how many factors, that this second factor, which is pretty small relative to the first one, I might force SPSS just to say, what would happen if you just gave me one factor? And I'll go ahead and show you how that works. I will go to extraction, just like I put in 6 before for the 6-item variable. I'm just going to say, give me one factor. I just want one factor in my model. If I leave rotation here, it's just going to give me a temper. Actually, I'll leave it in here so you can see the temper tantrum it'll give me. I'll just say, hey, you can't rotate because there's only one factor. One rotation, a factor rotated in space is already at its best rotation. You can't rotate it around to be any better fit. I click OK. That's that warning. If you ever see that warning, it's just you rotated a single factor, and it doesn't make any sense to change the single factor rotation. Everything else initially is going to be the same, except when I get down to that, which I extracted. It's just going to have extracted one factor. That factor accounts for 43% initially. It accounts for 41% after the communalities have been reduced. So it's still a very strong factor. And what I can now use that for is just like we used item total correlations. Item 1, if this were item total correlations, we say, well, oh, item 1 correlates 0.8 with the total score. It's the same thing, except it's a factor score now. So we say item 1 correlates 0.8 with my underlying factor. That's really strong. 0.69, very strong. 0.38, not bad. There's a correlation of 0.38. Item 9 has a small negative correlation. I don't like that. If I want one underlying total score or one underlying factor, imagine this is depression. Imagine this is, or, if you would prefer a mathematical ability, learning, whatever it is, spatial awareness, whatever the factor is, why would you want a negative loading or a 0 loading on this first factor? It doesn't make any sense. So we know we could do the same exact thing we did with reliability analysis, because this is a reliability analysis. We have an underlying factor we're interested in, whatever you want to call this factor. We'll call it a happiness scale. And we can look at the items, and we could go through just like we did in reliability analysis, and you could remove these one at a time. Like I could remove item 12 and then item 9 one at a time, and say, remove them and see what's left. I saw a hand flash up. I didn't catch who it was.
Yeah, it was me. You literally just answered it because I was like, oh, can you just remove the item and then and then you said it. So
yeah, here, for you all, and this is your actual homework assignment, the one I ran this on. So I just want, but please do it anyway, right? So I want you to have practice. You're going to go through, you're going to remove item 12, you're going to remove item 9, then you're going to decide whether or not you need to remove any others. And what's happening is you're cleaning your data. I'm going to tell you something that's not for your homework assignment, especially for those that work on survey instruments. Another thing this is useful for. Items that load high. Those are items that are correlated to the underlying factor you're interested in. Think of any factor for yourself, any factor you're interested in your research. Imagine that these data, imagine that this is that factor that you care about, motivation, happiness, whatever it might be. That means item 1 has a correlation of 0.811 with your underlying factor. And item 3 has a 0.87. And item 8, not bad, 0.38. But imagine your goal was reduce this down to like the minimum number of items you want to give on a survey instrument. You might say 20 items isn't so bad on a survey instrument. I will delete your survey instrument. I am not taking your 20 item survey. 7 items, you might catch me on a good day and I might click through 7 items. 10 items, 12 items, probably not. I mean, whatever the number is for you, just think of it. If it's possible, sometimes you can use factor analysis sort of the opposite way. We can say which items have the strongest relationship to the underlying factor. And if you imagine you were just trying to say, I only get 3 items. Just imagine you could only take 3 items and put it on your survey instrument from this survey. You might take the 3 that load the highest, or you might take a subset. You might take just say, hey, I'm going to get it down to 3, but I'll take the top 5 to 7 and look at them from a content expert perspective. So I might take, items 1, items 3, all of those that are kind of above 0.75 or above 0.8, and try and make a determination both mathematically and as a content expert about how to reduce down the number of items. These factor analysis is a very useful tool for both reliability and validity from a psychological perspective. The other reason I call this both reliability and validity is this. I said this in last class, but I want to end this class with these statements. The reliability of each item is here. This item has sort of its own reliability. That loading, that correlation, that tells me how reliable of an indicator it is for the factor I care about. That's a reliability measure. There's even ways, statistically we can use to create, we usually in confirmatory analysis, we can sort of aggregate these, find averages, however we do it, to say, what's the overall reliability similar to Cronbach's alpha? Another thing this is doing is validity. It's construct validity. And it's very clear when we go back to some of our models from earlier that if my expectation from a construct validity perspective is I designed an instrument for mathematical and spatial ability, these items should load on something that looks like mathematical and spatial factors. Otherwise, I have not confirmed my validity of the underlying factors. For example, if these arithmetic and digit span loaded on different factors and weren't correlated to each other, I might suspect I don't either have a good factor model or there's something wrong with my assessment to begin with, that it's not valid for the purpose I thought it was, and I did not uphold the construct validity of my data. This is literally a mathematical representation of construct validity. So what we've been doing all night is reliability and validity analysis through factor analysis. All right, I know I said a lot tonight. I'm going to take us out of, let's see, stop sharing a second. This is still recording. So again, what I'm going to do, just as the disclaimer, I'm going to take this, I'm going to make sure, hopefully this saves well. And what I'm going to do is I'm going to put it back on my YouTube site. I'm not going to put it as public. Please don't, for the rest of us, please don't share it as public. But you'll have access to it. You'll be able to, I'll put a link to it for us so that you can use this as you go through, but also for a learning experience. So that for those of you, these are the types of tools. Let me just tell you, this is the introduction of a tool that some people lean on as you go into things like your dissertation work, as you start looking at survey instruments. This is a tool that gets us beyond some of the basics and really into some advanced measurement issues. So from here, even if you don't take my advanced measurement course in the future, you've got a little bit of hints of what we're talking about, latent variable modeling, so that if you go into like, you want to do structural equation modeling, you're considering factor analysis, confirmatory factor analysis, latent variable modeling, diagnostic modeling, item response theory. This is the birthplace of all of those latent models that you would